Good afternoon. My name is Habib Ahmed, and the title of my dissertation is Investigation of Metal Modulated Epitaxy Ground III-Nitride High Power Electronic and Optoelectronic Devices. I would like to thank my advisor, Dr. Doolittle, for his wonderful mentorship throughout my PhD. I would also like to thank my committee members, Dr. Yoder, Dr. Kressler, Dr. Khan, and Dr. Vogel for their support during my dissertation process. In my PhD, I have focused on both gallium nitride and aluminum nitride pin diodes, which required individual scientific studies. This slide shows the sequence of topics which I'm going to follow. My scientific contributions to research include modeling, where I have shown gallium nitride pin diodes in MATLAB for optimized device design. I have demonstrated improved current distribution for quasi-vertical gallium nitride devices via Silvaco TCAD. From epitaxy point of view, I have established optimal MME growth conditions for different kind of applications. I've shown gallium flashing to mitigate surface contamination issue. I have shown controlled beryllium-doped gallium nitride semi-insulating films without surface segregation. I have achieved the first ever bulk P-type beryllium-doped aluminum nitride films. I have achieved approximately 6,000 times improvement in silicon-doped aluminum nitride electron concentration. From fabrication point of view, I have developed a novel fabrication method for high-power devices. I have achieved a record MBE quasi-vertical gallium nitride pin diode in terms of breakdown performance and in terms of Baliga's figure of merit. I have shown the first ever heterojunction P-type aluminum nitride on N-type gallium nitride based Schottky, pin, and junction Berry Schottky diodes. And finally, I have achieved the first ever homojunction aluminum nitride diodes. A PIN diode is a high voltage rectifier. It has faster switching as compared to the PN diode, and it's sensitive to photo detection. It's mostly used in radio frequency applications. My motivation for using gallium nitride based high power devices is that it has wider energy bandgap as compared to other semiconductor materials. It has higher critical electric field, which is important for high power devices because for both pin diodes and transistors, their figures of merit are proportional to their critical electric field. Also, gallium nitride has high electron mobility and saturation velocity, and the figure of merit for transistors is proportional to the saturation velocity as well. So, in terms of both figures of merit, for pin diodes and for transistors, gallium nitride has higher figures of merit as compared to the other semiconductor materials. Also, the figure of merit for pin diodes is inversely proportional to the on resistance, which is dependent on the band gap of the material. The higher the band gap, the lower the on resistance, and the higher the breakdown voltage, which is another motivation for my study of pursuing gallium nitride based pin diodes. Due to the compact size of gallium nitride, its applications range from commercial to avionics and defense. In this slide, I have shown the physics leading to the calculation of the breakdown performance of gallium nitride based pin diodes, which is dependent on the achievable depletion layer width, and that is further proportional to the background carrier concentration in the I layer of a pin diode. So the lower the background carrier concentration in the I layer of a pin diode, the higher the breakdown performance of pin diodes would be. And this is a key parameter. I'm going to show it later, but I have developed a method to achieve 2 orders of magnitude below the typical carrier concentration in gallium nitride pin diodes. Also, I've talked about the Baliga's figure of merit for pin diodes. It's proportional to the breakdown voltage and inversely proportional to the on resistance, which is further proportional to the band gap. So the higher the band gap, the lower the on resistance, and the higher the Baligas figure of merit for pin diodes would be. Typically, there are two kind of pin diodes. The fully vertical pin diodes, which are grown on top of bulk gallium nitride templates, and the quasi-vertical gallium nitride pin diodes, which are grown on foreign substrates. In terms of performance, the fully vertical gallium nitride pin diodes have much higher performance as compared to the quasi-vertical pin diodes. However, the fully vertical pin diodes are more than 20 times more costly as compared to the quasi-vertical pin diodes. And we know that cost is a major factor for high volume production. So this is the major motivation for me to pursue quasi-vertical gallium nitride based pin diodes. I've shown here in this plot that later I'm going to show it in my results. Our gallium nitride based pin diode, represented by the hexagonal star here in the plot, is comparable to the state of the art MOCVD best quasi-vertical gallium nitride pin diodes. And this is the only MBE based pin diode which is comparable to the state of the art pin diodes. And we are confident that we can further exceed the performance of these pin diodes. There are a few challenges by growing gallium nitride based pin diodes by using the conventional growth techniques. For example, an MOCVD has limited p-type doping, and also it is non-reproducible growing low-doped material. On the other hand, molecular beam epitaxy achieves intermediate levels of magnesium doped gallium nitride films, but it cannot grow low-doped material. Hybrid MBE MOCVD has also been tried, but it suffers from incorporation of contaminants. Another issue in quasi-vertical pin diodes is threading dislocations, leading to increased leakage currents and reducing the breakdown performance of these devices. Also, from fabrication point of view, it has been found that there is high current flow along the mesa edges, reducing the breakdown performance of these devices. Metal modulated epitaxy is a novel growth technique that, in combination with device design optimization, can address all these challenges. Metal modulated epitaxy is a modified MBE growth technique in which the metal fluxes are shuttered while keeping the nitrogen flux constant. It utilizes metal-rich fluxes to enhance metal add flare mobility at low growth temperatures, achieving high uniformity and high quality films as compared to the typical MBE. Some of the major achievements of metal modulated epitaxy include hyper p-type doping of approximately 40 times higher as compared to the other growth techniques for gallium nitride, aluminum gallium nitride, and indium gallium nitride. It also achieves high control of ternary alloys. Furthermore, MME achieves a growth rate up to approximately 10 microns per hour, and it exceeds the growth rates of both MOCVD and MBE. This makes MME suitable to grow thicker eye layers in high power devices, which is the field that I want you to pursue. I talked about the challenges in gallium nitride pin diodes, and in this slide I'm going to talk about some of the solutions that MME offers for those challenges. The first solution is MME achieves hyper p-type doped gallium nitride films, and I'm going to show it later that we have achieved 2 orders of magnitude lower doping for the eye layer in pin diodes. Also, in another study I'm going to show that we have achieved high quality films which are limited by the template quality, not by the regrown film quality. And I have investigated simpler designs by Silvaco TCAD in line with MME to mitigate the high current along the mesa edges issue. Now I'm going to transition towards my results. My first study is Comprehensive analysis of the 3D phase diagram of metal modulated epitaxy grown gallium nitride. In traditional MBE, we observe huge variations in the effective gallium flux, and for example, in traditional MBE at a substrate temperature of 740 degrees C, a 1.5% change in the substrate temperature would result in the corresponding flux change of approximately 50%. This non-uniformity is due to desorption in MBE at higher growth temperatures. MME, on the other hand, achieves excellent uniformity and thickness control because it operates below the desorption regime. In traditional MBE, the growth parameters are substrate temperature and 3:5 ratio. MME is more complex as compared to the traditional MBE because in MME we also have an additional growth parameter, which is excess gallium dose per shutter cycle. So I wanted to study the effect of each growth parameter of MME on the quality of the films, but as a first step, I wanted to improve on the template cleaning. So from one of my sim studies, I found that there is a high level of oxygen from the diffusing from the regrowth interface or films. So I used a method of gallium flashing, which is adsorption of gallium at a lower substrate temperature and desorption at a higher substrate temperature. And by using this technique, I saw improvement both from read intensity transients and also from SIMS. I was able to achieve improvement of more than 1 order of magnitude in terms of regrowth interface cleaning. And this is significant for both p-type gallium nitride films and also for unintentionally doped gallium nitride films for pin diodes. Then I studied the effect of the first growth parameter, which is substrate temperature, in the range of 500 to 750 degrees C, and I found the best morphological and electrical quality films at a substrate temperature of 650 degrees C. From X-ray measurements, we found that our regrown films match the quality of the template above 600 degrees C. However, below 600 degrees C, we found added defects. This temperature window is approximately 100 degrees C below the traditional MBE growth temperatures, making MME more suitable for commercial use. Transmission electron microscopy measurements also validated the X-ray measurements, where we found that the MME films match the template quality above 600 degrees C. However, below 600 degrees C, we found added defects in the regrown films. And optical quality was found to be the best at 650 degrees C. So I fixed the substrate temperature at 650 degrees C, and now I wanted to study the effect of excess gallium dose per shutter cycle, which is our second growth parameter. I want to introduce excess gallium dose first. So in metal modulated epitaxy, we start from a stable surface, then we open our shutter, which results in adsorption of gallium in multiple stages, and excess gallium dose is the gallium surface coverage during the MME shutter open time per cycle. So I studied the effect of excess gallium dose from 3/4 of a monolayer to 48 monolayers, and from this study I found that we achieve step flow surface morphology above 6 monolayers excess gallium dose. Also, from X-ray measurements and validated by transmission electron microscopy measurements, we found a trend of improvement in crystal quality with excess gallium dose in the individual pre-bilayer coverage regime and also in the droplets regime. However, film quality was found to be the worst near bilayer coverage, which is totally opposite result as compared to the traditional MBE. And we also found from optical measurements that the optical quality is the worst near bilayer coverage, but for the remaining growth conditions, the optical quality was even better as compared to the template. Then I fixed the excess gallium dose at 12 monolayers open time, and I studied the effect of 3:5 ratio in the range of 1.3 to 2.8. And from electrical structural and optical measurements, we found that the 3:5 ratio of 1.3 gives us the best results. And also in terms of electron concentration, it gave electron concentration of 10 to the power of 16 per centimeter cube, a significant result for p-type doping and also for high power devices. To summarize the key results, I introduced a gallium flashing technique to improve on rigorous interface cleaning for UID gallium nitride films and also for p-type films for pin diodes. I found the best growth conditions in MDE are not necessarily the optimal for our MME growth technique, and I demonstrated the optimal growth conditions at approximately 100 degrees C below the traditional growth temperatures, making MME suitable for commercial use. Furthermore, I found the optimal growth conditions for my pin diodes. So next I wanted to focus on the I layer of pin diodes. I wanted to reduce the background doping concentration to achieve higher breakdown performance for pin diodes. In this regard, I performed a study on beryllium-doped abrupt semi-insulating MME gallium nitride for high-power device applications. Now the first question arises, iron and carbon also results in semi-insulating films. So why can we not use iron and carbon for the I layers and pin diodes? The answer to that question is that both iron and carbon have high sheet resistance, which are not suitable for I layers and pin diodes. And also, both have multiple donor and acceptor levels inside the bandgap of gallium nitride, leading to increased leakage currents and reducing the breakdown performance. On the other hand, I'm going to show it later that beryllium has suitable sheet resistances for pin diodes, and it has been shown that it only has acceptor levels inside the bandgap of gallium nitride. So we would still have a significant portion of the semiconductor to control leakage current. Initially, the theoretical activation energy of beryllium and gallium nitride was thought to be 60 millielectron volts. However, later experimental studies showed its activation energy in the range of 500 to 700 millielectron volts. So beryllium is actually a deep acceptor in gallium nitride that could be used for semi-insulating applications. Previous studies of beryllium-doped gallium nitride resulted in semi-insulating films, but they suffered from beryllium surface segregation. However, for devices, we need controlled dopant profiles to control the electric fields in devices. So my motivation for this study was to utilize the improved growth kinetics of MME to eliminate that surface accumulation issue of beryllium and gallium nitride. So in this regard, I grew beryllium-doped gallium nitride films with beryllium doping levels of mid 10 to the power of 17 to 1 into 10 to the power of 20 per centimeter cube. And I achieved beryllium step-doped gallium nitride profiles for the first time. And these profiles show sharp rate of rise and rate of fall. Then I grew several samples of beryllium-doped gallium nitride in the beryllium doping range of mid 10 to the power of 18 to low 10 to the power of 20 per centimeter cube. And I achieved sheet resistances in the range of 10 to the power of 5 to 10 to the power of 7 ohm per square, which are suitable to be used as I layers in pin diodes and also as buffer layers in transistors. The carrier concentrations of these films were in the range of 10 to the power of 14 to 10 to the power of 15 per centimeter cube, suitable for I layers in pin diodes. Semi-insulating control beryllium-doped gallium nitride films are suitable to be used as buffer layers in transistors because conducting buffer layers would result in poor pinch-off characteristics. And on the other hand, controlled semi-insulating films would improve the pinch-off characteristics of transistors. To summarize the key results, I achieved controlled semi-insulating beryllium-doped gallium nitride films without surface segregation for the first time. And these films have the potential to be used as buffer layers in transistors and also as I layers in pin diodes. So next, I wanted to focus on gallium nitride pin devices, but the plan was to grow thicker gallium nitride pin diodes in the range of 3 microns to 13 microns, and that required an optimized fabrication process as well. So I performed a study on cascaded nickel hard mask to create chlorine-based ICP dry-etched deep mesas for high-power devices. In this regard, I performed a study on 5 different kind of masks. The first one is positive photoresist, but I found its gallium nitride to mask selectivity to be very low, not suitable for our case. Then I studied E-beam evaporated nickel hard mask, but its yield was approximately 40%, once again not suitable for our study. Later, I performed a study on electroplated nickel hard mask. Its selectivity was high, but it is time inefficient and also its chemical waste is expensive to dispose of. Later, I studied sputtered nickel hard mask. Its yield was 100% and its selectivity was high, but it caused damage to the underlying gallium nitride films. So finally, I devised a novel procedure of nickel hard mask in which I first deposited a 50 nanometers of E-beam evaporated nickel followed by 2 microns of sputtered nickel. It resulted in 100% yield, high gallium nitride to mask selectivity, undamaged underlying films, and I was able to successfully apply it to my thicker actual gallium nitride pin devices. And with this technique, we can also achieve thicker mesas. So finally, I performed my major study in this regard, which is beryllium-doped gallium nitride I-layer-based high-power pin diodes achieving large quasi-vertical MBE breakdown performance. I've talked about these points where I found the optimal growth conditions, I found the optimal I layers, and I found the optimal fabrication conditions for the thicker devices. I still needed to tackle one issue, which is to take care of the high current flow along the mesa edge and to demonstrate a better design. So I've shown this that due to high current flow along the mesa edge, there would be premature breakdown of the devices. So I investigated simpler designs using Silvaco TCAD and applied them in MME growth. In this regard, I did a comparative study of 2 pin diodes, both with I-layer thicknesses of 10 microns. The difference between these two is that the right structure has a thin 50 nanometers of beryllium doped gallium nitride film sandwiched between the n-type layer, which would introduce a small barrier, resulting in more uniform current distribution across the device. So as we can see that the current distribution improves from approximately 40% to 100% of the p-type contact of the device. And later I have shown in one of my devices that now the breakdown occurs across the bulk of the device and not along the mesa edge. Then I grew these gallium nitride pin diodes. This slide shows a layer structure diagram of my devices, where first I sandwiched a beryllium doped gallium nitride film inside the n-type layer, and the beryllium doping was 1 into 10 to the power of 17 per centimeter cube. And then I grew beryllium doped gallium nitride I layers with I layer thicknesses of 1, 2, 5, and 10 micrometers. And I kept the transition layer between the n-type and the I layer to be graded junction for improved breakdown performance. Later, I deposited magnesium doped gallium nitride top layer with a cap layer as well. And once again, I kept the transition from the I layer to the p-type layer is graded for improved breakdown performance. From CV measurements, we found carrier concentration of 8 into 10 to the power of 16 per centimeter cube. And from plotting the equations given in the previous slides and this carrier concentration represented by the dashed line, the achievable depletion layer width is approximately 2.4 microns, and the achievable theoretical breakdown performance is 450 volts with achievable on resistance of approximately 10 to the power of minus 5 ohm centimeter square. From CTLM measurements, the N-type contacts showed contact resistance of approximately 8 10 to the power minus 6 ohm centimeter square, while the P-type contact showed contact resistance of approximately 3 10 to the power minus 3 ohm centimeter square. The P-type contact resistance is slightly higher because I performed the annealing of both types of contacts at 700 degrees C. So this annealing temperature is slightly non-optimal for the P-type contact, but this can be improved. However, in the current case, this would contribute to relatively higher specific on resistance of the pin diodes. In this slide, I have shown the JV characteristics of my pin diodes for eye layer thickness of 1 micron, 2 micron, 5 microns, and 10 microns. And I've shown the maximum breakdown performances of each individual kind of devices as well. And the maximum breakdown voltage of 375 is a record breakdown voltage for gallium nitride based pin diodes grown via molecular beam epitaxy. One significant point that we see from comparison of the thicker devices versus the thinner devices is that the thicker devices show leakage current which is significantly lower, approximately 7 orders of magnitude lower as compared to the thinner devices. So we used a doping of 1 into 10 to the power of 17 per centimeter cube and achieved carrier concentration of 8 into 10 to the power of 16 per centimeter cube. And by comparison of our breakdown performance with the state-of-the-art quasi-vertical devices, we are comparable to the best MOCVD ground quasi-vertical devices, and we are the only group which are in the state-of-the-art MBE performance in terms of quasi-vertical devices. We achieved record breakdown performance and also record Baligas figure of merit for MBE ground quasi-vertical devices. So I've shown that we have used a carrier concentration of 8 into 10 to the power of 16 per centimeter cube, resulting in depletion layer width of 2.4 microns. So our achievable breakdown performance is limited by the carrier concentration. However, we can further lower the carrier concentration, and I've shown we can do that. And by doing that, we can extend the performance of these pin diodes to even surpass the best quasi-vertical and quasi-vertical MOCVD based devices. So now I'm going to talk about my second pin diodes based study, which is aluminum nitride based pin diodes. The breakdown field of semiconductors is scales with the bandgap of semiconductors, and we know that the critical electric field of aluminum nitride is approximately 3 times that of gallium nitride, resulting in a theoretical improvement in terms of Baligas figure of merit for aluminum nitride over gallium nitride of approximately 17.5 times. Some exciting applications of aluminum nitride based devices are operation in extreme environments, high temperature electronics and sensors, power distribution, and high power radio frequency electronics. Some other amazing applications of aluminum nitride include deep UV LEDs and lasers, solar blind detection, and acoustic devices. My major motivation for this study is that aluminum nitride ranks in the top 2 materials in terms of ultrawide bandgap semiconductor performance parameter. For example, the critical electric field of aluminum nitride is 1.5 times that of gallium oxide, 3 times that of gallium nitride, and approximately 5 times as compared to that of silicon carbide. But up to now, the major limitation was uh, p-type doping, the lack of doping in aluminum nitride. And we first proposed the rhythm-doped aluminum nitride p-type films grown via metal modulated epitaxy. So I performed a study on first-time achievement of p-type aluminum nitride films via beryllium doping. The solubility limit of a dopant is determined by the formation energy of the dopant. Formation energy further depends on the atomic radii matching and the bond strength of the host versus dopant atoms. We know that in case of gallium nitride, magnesium closely matches in terms of atomic radius with the radius of gallium in gallium nitride, so it is found to be the best p-type dopant in gallium nitride. By similar hypothesis, beryllium closely matches with the atomic radius of aluminum in aluminum nitride and is potentially the best candidate as a p-type dopant in aluminum nitride. Generally, the theory agrees that the activation energy of beryllium is lower as compared to the activation energy of magnesium in aluminum nitride. The activation energy of beryllium in aluminum nitride is found to be approximately 300 milli-electron volts. In traditionally grown magnesium-doped gallium nitride, we find isolated impurity levels, which is also depicted by its two peaks in photoluminescence measurements. Now, on the contrary, in metal modulated epitaxy, we can achieve high solubility, and also we achieve impurity band formation overlapping the valence band of the semiconductor, which is also depicted by a single photoluminescence peak where the band overlaps that of the gallium nitride 3.4 electron volts band gap. So we have achieved an improvement in terms of activation energy for magnesium-doped gallium nitride, reducing it from 200 to 50 milli-electron volts as compared to literature. So now we wanted to see if we can improve the activation energy of beryllium in aluminum nitride as well. This led to my study of growing beryllium-doped aluminum nitride on top of HVPE aluminum nitride templates with buffer layers. We achieved streaky reflection high energy electron diffraction patterns indicating smooth surface morphology. From AFM comparison of a beryllium doped aluminum nitride versus undoped control sample, we see that beryllium doping improves the surface morphology. Later, I deposited platinum, palladium, gold contacts on these films for Hall measurements. And from extensive optimization of the contacts, here I've shown a comparison of the post-annealed beryllium-doped aluminum nitride versus pre-annealed contacts. And the annealing improves contacts conductivity by approximately 6 orders of magnitude. Furthermore, from comparison of a beryllium-doped aluminum nitride versus annealed undoped aluminum nitride film, we see an improvement in approximately 4 orders of magnitude. So it's actually the beryllium doping which improves the conductivity of these samples. Later, I wanted to validate the conductivity type of these samples with both Hall measurements and also hot probe measurements. But first, I calibrated Hall and hot probe measurements for our standard p-type, UID, and n-type gallium nitride samples. Later, I grew beryllium-doped aluminum nitride samples at a substrate temperature of 600 degrees C at different beryllium doping levels. Beryllium doping levels where the Hall results were questionable. Beryllium doping levels where we see massive compensation. And beryllium doping levels where we achieve reliable results in the range of 10 to the power of 15 to mid 10 to the power of 17 per centimeter cube, resulting in activation efficiency of approximately 5%. I also grew beryllium doped aluminum nitride at 700 degrees C growth temperature and achieved even higher hole concentration of 3 into 10 to the power of 18 per centimeter cube. And the conductivity type was also validated from hard probe measurements. Later, we sent these samples to Lakeshore for conductivity confirmation and also for temperature-dependent Hall measurements to extract the activation energy of these samples. And we found a very low activation energy of 37 milli-electron volts. To summarize the key results, we at Georgia Tech are the first experimental group to report success in achieving P-type aluminum nitride films with a very low activation energy of 37 milli-electron volts. We have achieved as high as 3 into 10 to the power of 18 per centimeter cube hole concentrations. And we believe that with this achievement, aluminum nitride is no longer just an insulator or substrate. It has graduated to a semiconductor. Then we wanted to apply the P-type aluminum nitride to devices, but at that time, we did not have a source of N-type aluminum nitride inside our MBE chamber. So I performed a study on P-type aluminum nitride-based heterojunction diodes with Schottky, pin, and junction barrier Schottky character, achieving significant breakdown performance. Schottky diodes have the advantage of low turn-on voltage, but they also have low breakdown performance. Pin diodes have higher breakdown performance, but also higher turn-on voltage. Junction barrier Schottky, or JBS, is a new kind of diode which has advantages of both Schottky and pin. It has low turn-on voltage and also high breakdown performance. Currently, there are two approaches for conventional JBS diodes. One involves ion implanted P-type regions, but it requires activation of the dopants. Another approach requires etched and patterned P-type regions, and it suffers from high etching damage. So we introduced a novel approach to grow MME Schottky, pin, and junction barrier Schottky diodes. We know that the lattice mismatch between aluminum nitride and gallium nitride is approximately 2.4%, and above a certain critical thickness, the growth of aluminum nitride and gallium nitride is going to result in high crack density. So we utilize the intentional crack density of aluminum nitride and gallium nitride to grow novel Schottky, JBS, and pin diodes. And this figure shows the layer structure diagram of my growth structure. We have an N-type gallium nitride film, then an I-type gallium nitride film, and then beryllium doped P-type aluminum nitride film. And the crack density of the top film is controlled via beryllium doping and growth conditions. The density of the deep and wide cracks determines the behavior of the diode. High density of deep and wide cracks resulted in Schottky behavior. Films with no open cracks resulted in pin diode behavior, and films with medium density of deep and wide cracks resulted in junction barrier Schottky behavior. Here I am showing the JV characteristics both forward and reverse of these diodes. These are representative figures. We see that for the Schottky diodes, we observe low turn-on voltage, but also low breakdown performance. For the pin diodes, we see high turn-on voltage and high breakdown performance. And for the junction barrier Schottky diodes, we achieve a low turn-on voltage of 1.5 volts and a high breakdown voltage of approximately 20 volts. And from early quasi-vertical electric fields are demonstrated in these devices, we achieved a field of approximately 1.25 megavolts per centimeter, which is at the high end of MBE achievable breakdown critical electric field performance, both in case of quasi-vertical and also in case of fully vertical devices. In the previous slide, I have shown representative results. However, we have shown results for multiple samples and multiple devices, which are summarized in this slide. Next, I wanted to pursue a research journey towards homojunction aluminum nitride, and in this regard, we introduced silicon material into one of the effusion cells in our MBE chamber. Silicon, we know that is a shallow donor in gallium nitride with activation energy of 17 millielectron volts. However, with increase in aluminum content in aluminum gallium nitride, its activation energy increases to above 200 millielectron volts. So although the atomic radius of silicon closely matches with aluminum in aluminum nitride, but due to several reasons, for example, formation of aluminum vacancies, DX formation, which is transition of silicon from shallow to deeper states, and threading dislocations, the activation energy of silicon in aluminum nitride is high. So I utilized the high crystalline conditions of MME, and I grew silicon doped aluminum nitride films in the doping range of 5 10 to the power 17 to 7 10 to the power 19 per centimeter cube, and I achieved a high electron concentration of 6 into 10 to the power 18 per centimeter cube, which is 6,000 times higher as compared to the previous best electron concentrations in silicon doped aluminum nitride. So now the stage was set to perform the final study, which is first time homojunction aluminum nitride diodes. This slide shows the layer structure diagram of these diodes, where I grew the N-type aluminum nitride and the I-type aluminum nitride, which are silicon doped at 800 degrees C substrate temperature, and I grew the P-type beryllium doped aluminum nitride at a substrate temperature of 700 degrees C. From PTLM comparison of a planar P-type film versus the PTLM on the device, we see that our current conductivity was slightly lower as compared to the planar film, but they were still comparable. However, for the N-type aluminum nitride device contact, our current conductivity was 2 to 3 orders of magnitude lower as compared to the planar film. We suspect that this is due to the damage introduced during the etching process. I repeated this study, but once again I encountered the same issue, and this is something which requires improvement in the future. In this slide, I've shown the JV characteristics, both forward and reverse bias, for these homojunction aluminum nitride diodes. I achieved approximately 7 orders of magnitude rectification for these diodes, and we achieved a nearly ideal turn-on voltage of approximately 6 volts for a 6.1 electron volts semiconductor. However, we see a high series resistance evident from the long tail of the semilog plot, which is attributed to the high N-type contact resistance, and with improvement in the contacts, we can achieve even higher performance for these devices. To summarize my key results, my scientific contributions include modeling, where I've shown gallium nitride tin diodes in MATLAB for optimized device design. I've demonstrated improved current distribution for quasi-vertical gallium nitride devices via Silvaco TCAD. From epitaxy point of view, I have established the optimal growth conditions for different device applications. I've shown gallium flashing to mitigate surface contamination. I've achieved controlled beryllium-doped gallium nitride semi-insulating films for different applications. I've achieved the first ever P-type bulk aluminum nitride films. I've achieved approximately 6,000 times improvement in electron concentrations in silicon-doped aluminum nitride. From fabrication perspective, I've developed a novel fabrication method for high-power devices. I've achieved a record MBE quasi-vertical breakdown performance and also Baliga figure of merit for gallium nitride pin diodes. I've achieved the first ever heterojunction p-type aluminum nitride on n-type gallium nitride based Schottky pin and junction barrier Schottky diodes. I've achieved the first ever homojunction aluminum nitride. This slide shows a list of my first author publications, contributing author publications, invited talks, conference presentations and posters, continued, conference papers, invention disclosures, and book chapters. I highly acknowledge my advisor, Dr. Doolittle, for extending his support both in person and technically, for his wonderful advising, for helping us in different situations to expedite our research, for managing financial resources for us in terms of equipment and also in terms of materials. Some of the material that we are working on is pretty expensive. Beryllium would cost $5,000, more than that, per gram. For our trainings, I really appreciate it, and I'm looking forward to working with him in different capacities in the future as well. I would like to thank my committee members, Dr. Yoder, Dr. Kressler, Dr. Khan, and Dr. Vogel for their valuable time. It's a busy time of the semester, and they had to make special arrangements to make it to the dissertation, and I really appreciate their support in my dissertation process. I highly acknowledge my group members. They helped me throughout my studies in different capacities. And finally, since my work involved extensive fabrication for which I needed to use the cleanroom facilities, I really appreciate all the help that I received from the staff members of the clean rooms. They went above and beyond their official duties to help me in so many different situations. I'm feeling bittersweet, getting close to what is concluding my PhD. I'm happy that I'm finishing up, but at the same time, I'm sad that I'm leaving. Thank you so much for your kind attention, and now I would like to request Dr. Doolittle to chair the proceedings.